Welcome to the Explainer. Today, we're going to demystify the logarithmic graph. You know, that swooping curve that seems to pop up everywhere? Well, it holds the key to understanding a ton of stuff, from financial growth to scientific measurements, and we're going to break it all down.
So let's kick things off with a practical question. An exponential formula is great for telling you your final balance after, say, 10 years. But what if the question is flipped? What if you know the destination, doubling your money, but you need to find out how long the journey takes? Yeah, that's a totally different kind of problem, and for that, you need a different tool.
And that's where logarithms come in. They're basically designed to work backwards, to find the cause, like time, that leads to a certain effect, like your bank balance doubling. To really see this relationship, we need to visualize it. And that means we need to understand the graph of a logarithm.
But hold on. Before we can even think about putting pen to paper or pixels to screen, we have to talk about the single most important rule of logarithms. It's a fundamental limitation, a golden rule that shapes every single log graph you will ever see. Every function has what we call a domain. It's just a kind of fancy way of saying all the numbers you're allowed to plug in for x. For a lot of functions, you can plug in anything you want. But logarithms, well, they have a very, very strict bouncer at the door. Okay, now this is where it gets really cool. A logarithm is the inverse of an exponential function. And look what happens here. The domain and range just completely swap places. For log function, the input, your x value, can only be a positive number. You just cannot plug in 0 or negative. Period.
So what does this positive numbers only rule actually do to our graph? Well, it creates this invisible barrier, kind of like an electric fence. It's a vertical line that the curve will get closer and closer and closer to, but it will never ever touch it or cross it. We call this barrier a vertical asymptote. And you know what the best part is? You can always figure out exactly where this barrier is with a super simple 3-step process. You just take whatever's inside the log's parentheses, set it to be greater than 0, and solve for x. That's it. It works every single time and tells you the function's domain. All right, so let's get our hands dirty and actually build the blueprint for this thing. We're going to start with the most basic or parent log graph. Once you understand this core shape, you can move it, stretch it, and flip it any way you want. Remember how we said logs and exponentials are inverses, like mirror images of each other? Well, this is what that looks like. We can literally just take the points from an exponential graph and swap the x and y coordinates. See that? The 0.24 on the exponential becomes 4.2 on our log graph. It's that simple. And when you plot these swapped points, you start to see the non-negotiable features of every basic log graph. 1, it's got that vertical barrier right at x equals 0. 2, it always crosses the x-axis at the point 1, 0. And 3, it always passes through the point b, 1, where b is just the base of your logarithm. Okay, so we've got the blueprint down. Now for the fun part. Let's start moving it around. Because honestly, most of the log functions you'll see are just shifted or stretched versions of this parent graph we just built. Now, you can do a bunch of things to this graph. You can shift it up or down, you can stretch it, you can flip it over, but the single most important change is the horizontal shift. Why? Because it's the only one that actually moves that fundamental barrier, the vertical asymptote, and changes the entire domain of the function. And here is the rule you have to burn into your brain. It all comes down to that little number c that's added or subtracted inside the parentheses. But you gotta watch out because it's a little backwards from what you might think. A plus c actually moves the graph to the left, and a minus c moves it to the right. This means the new vertical asymptote is always at x equals negative c. Okay, let's put this rule to the test. Let's see it in action. We've got a log base 3, and inside the parentheses, we're subtracting 2. So based on the rule we just learned, what's going to happen here? Exactly! Because our c is negative 2, the entire graph, the whole shebang, just scoots 2 units to the right. That means the vertical barrier moves from x equals 0 over to x equals 2. The domain is now all numbers bigger than 2. And every single point on the graph, like that key point 3,1, just slides right over 2 spots to become 5,1. So let's zoom out. What does this all mean when you see a log graph out in the wild? It means you can actually work backwards. You can look at its key features and figure out the exact function that created it. This table is basically your cheat sheet. It sums up all the ways you can transform that parent graph. But what's the first thing you should always look for? That's right, the horizontal shift. It tells you where the function lives by defining its domain and that all-important vertical asymptote. You know, we started with this idea, and now we can actually see it. The graph is literally a picture of that cause and effect relationship. You can pick any effect you want on the y-axis, trace it over to the curve, and then drop straight down to find the exact cause on the x-axis that produced it. It's pretty powerful.
At the end of the day, this isn't just some abstract concept from a math book. The shape of the logarithm is hidden in plain sight all around us. It describes everything from population growth and radioactive decay to the Richter scale for earthquakes. The graph tells a story. And now you know how to read it.